Okay, good afternoon. We're going to go ahead and get started. Today, the live chat will focus on the chain rule unless I receive some other questions. Before we get started on the chain rule, though, I did receive a good Ask My Instructor question. I love to receive Ask My Instructor questions, and let's take a look at this one. This was from Chapter 3, Section 5, item number 51 in our Calculus 1 class, and it looks like this. So direct your attention to the left side of the screen for the moment. Find the limit of the following. And they give us the limit as theta approaches pi over 6 of, and then we have this big expression here that we're taking the limit of, sine of theta minus a half over theta minus pi over 6. So if you go back to Chapter 2, Section 4, item number 25, I worked an Ask My Instructor question for that one, and it asks us to use this fact that the limit as theta goes to 0 of sine of theta over theta is equal to 1. Now that works whether you have theta or you have alpha or you have, in this case, theta minus pi over 6, as long as the argument of the trig function here matches the expression in the denominator below. And as long as that expression is approaching 0. So it would be really nice if we had the limit of as theta minus pi over 6 goes to 0. And we had sine of theta minus pi over 6 over theta minus pi over 6. We don't, of course. In the numerator, we have just a theta in the argument of sine. And we have this minus a half tagging along out there. So that's not quite the form we want to. So when I look at this, I wonder, can we get closer to this? And how might we go about doing that? So I noticed that a half was in the numerator, separate from the sign. Keep in mind, since it's not in parentheses, it's not sine of the whole theta minus 1/2. No, it's just sine of theta, and then we have this minus a half outside of the argument. So I was thinking, what do you take the sine of that would give you a half? And it just so happens sine of 30 degrees is a half, or in other words, sine of pi over 6. So I was thinking, let's go ahead and replace the 1/2 with sine of pi over 6. So I did that. And if I do that, I now have sine of theta minus sine of pi over 6. So I thought, well, what's a trig identity that has a difference of two signs? And the one that I found is sine of u minus sine of v equals 2 times cosine of u plus v over 2 times sine of u minus v over 2. So in our case, the u would be the theta and the v would be the pi over 6. So I plugged in just to see what would happen. And you can't be afraid to do that. You know, you got to just try things and see what works. And so what happened was I got 2 cosine theta plus pi over 6 over 2 sine of theta minus pi over 6 over 2. All over theta minus pi over 6. I've still got the limit going on out front here like before. So then I thought, well, I'd really like, again, I'm going to scroll back up just to remind you, I'd really like it to look like sine of something over that thing, so the limit as theta goes to 0 would turn out to be 1. But I have a cosine and a sine, but I thought, hey, I could separate this and have 2 cosine of that argument times, and then just have the sine over the theta minus pi over 6. And this would be very close. It's almost what we need, but in order for the angle in the argument to match the denominator, we would need the over 2 part. So I did a little adjusting. I said, well, to get over 2, I'd have to multiply both the numerator and denominator by 1/2. You know, I can't multiply just because I want to, but if I multiply by 1, I'm good, right? So I multiplied by 1/2 over 1/2. And then the top 1/2, and I just put in front. It could go in the numerator of this fraction, but I just put it in front because it means the same thing. And the denominator 1/2 ended up multiplying times theta minus pi over 6, so I got what I wanted. That's by design. So the next thing that I did was I said, okay, so I don't have theta minus pi over 6 over 2 matched with theta minus, or let me say it a different way. It wasn't quite what I expected. I got theta minus pi over 6 over 2 instead of just theta minus pi over 6, but it still works. It still is the same argument as the expression in the denominator, but then I have to deal with this. Because remember, what I need is for theta minus pi over 6 over 2 to go to 0. All right, so I know that if theta is approaching pi over 6, that means theta minus pi over 6 is approaching 0. But if I divide both of those expressions by 2, that means that theta minus pi over 6 is approaching 0 over 2, or just 0. So really, this is the situation in that I wanted to imitate. So it's still the case that the limit as theta minus pi over 6 over 2, or sorry, minus pi over 6 over 2, as that goes to 0, then the sine of theta minus pi over 6 over 2 over theta minus pi over 6 over 2. This guy is going to go to 1. So I forced it to fit the pattern. All right, so now that means that I can separate it into 2 limits. When both limits exist and are finite numbers, you can just break it apart into the product of the limits rather than the limit of the products. So I plugged in pi over 6 to my cosine to evaluate this limit, and this limit I knew was just going to be 1. So we have cosine of 2 pi over 6 divided by 2, which is just pi over 6, times 1, which has no effect. So it's just the cosine of pi over 6, which is root 3 over 2. So that's the solution to the problem 3.5.51. It's just root 3 over 2. And the way we got it was by manipulating the expression until it fit this pattern. All right, now we're going to go to talk about the chain rule. And the chain rule is really powerful stuff. It allows us to take a function like y equals, for example, let's say let me redo that. 3x plus 5 squared, and take its derivative without having to FOIL it all out. We already know how to take the derivative of y equals u squared, right? So in this case, dy du, we would use the power rule, and we'd bring 2 out front, and we'd subtract 1 from the power, and we would just get 2u. So you might think that the derivative of y with respect to x here, that we would do the same thing, but we can't, because this 3x plus 5 is not the variable that we're differentiating with respect to. So what we have to do is we have to compensate for the fact that this is actually a composition of functions. Instead of having x squared, we have, or u squared, we have 3x plus 5 squared. So what we do is we say, okay, I'm going to pretend like that's an x for the moment. So I'm going to bring the power out front, And I'm going to subtract 1 from it. But then to compensate for the fact that it wasn't just an x, I'm going to multiply times the derivative of what it was. So we get dy dx equals 2 times 3x plus 5 times the derivative of 3x plus 5, which is just 3. Now notice that that would give us dy dx equals 6 times 3x plus 5, or 18x plus 30. So I just want to confirm that this is actually correct by multiplying out the 3x plus 5 squared and showing you that you would still get the same derivative with respect to x. So, and the way we would have done it previously is we would have said, well, y is really 9x squared plus 30x plus 25 if we FOIL that out. And so taking the derivative, dy dx would be 18x plus 30. All right, but this is actually easier, right, than applying this new idea of the chain rule. But unfortunately, in a lot of situations, we don't have the choice of multiplying it out. So in that case, we would have to use the chain rule. The chain rule says that if you take the derivative of a composition of functions, f of g of x, where g of x is the inner function, then that's going to be the first derivative of f, the outer function, with the g of x plugged into it, times the derivative of g, the inner function. If you look at what I did for y equals 3x plus 5 quantity squared, the inner function is the 3x plus 5. So what this first part, f prime of g of x, is saying is just leave that 3x plus 5 alone and take the derivative like you would have had that 3x plus 5 not been there. So you're going to just bring the power up front, subtract 1 from it in this case because we have a power situation. And then go ahead and multiply by the derivative of the inner function. Let me highlight that in blue here. So the derivative of the inner function is this part here. So you differentiate when you have one function plugged into another. You can differentiate the outer function, but just leave the inner function plugged into it, and then multiply times the derivative. That's the same as what I was saying, which is to compensate for the fact that it wasn't just an x or just a u, that we have to multiply times the derivative of whatever it was. Okay, let's look at another example. So, in this example, we're going to use the chain rule to differentiate, or in other words, to find the derivative. In part A, we have y equals the square root of 3x squared minus x plus 1. All right, so what if it had been y equals u, or the square root of u, I should say. What if it had been just y equals the square root of u? How would you find dy du? So if that had been the case, you would first, we don't have a rule for square roots, but we do have a rule for powers. So you would change it from the square root notation to the 1/2 power notation. Then you would bring the power out front and subtract 1 from it, giving you 1/2 u to the negative 1/2. Which, by the way, if you wanted it written in radical notation, you would have to first bring the u to the negative 1/2 down into the denominator, change it to a positive exponent, and then dy du would be equal to 1 over 2 times the square root of u. All right, so that would be a type of derivative we could have found before the chain rule. We're going to do a very similar thing here. It's just that we're going to keep this 3x squared minus x plus 1 in there as if it were u. but then we're going to compensate for it not being u by multiplying by its derivative. So first we rewrite it algebraically as 3x squared minus x plus 1 to the 1/2 power. And then to take the derivative, we're going to take the power out front, leave the base the same, subtract 1 from the exponent, and then multiply by the derivative of what's inside 3x squared minus x plus 1. So that's going to be y prime equals 1/2 3x squared minus x plus 1 to the negative 1/2 times, now the derivative of 3x squared would be 6x, the derivative of negative x would be negative 1. Alright, so this is our derivative, but it's just not in a pretty format. So as I did with the smaller function that didn't require the chain rule, I'm going to rewrite it. We're going to bring the negative exponent down into the denominator, change it to a positive. Okay, notice that that 6x plus 1 is like a whole number being multiplied by a fraction, so it just multiplies into the numerator. So we have y prime equals 6x minus 1 over 2 times 3x squared minus x plus 1, and I'm going to change that to a square root just to be consistent. Alright, so we have our final answer. Now, what I would like to do is to, that one required the chain rule just like, it required the chain rule version of the power rule, just like the exercise before. Let's do one that uses a different derivative rule than the power rule, because it can be any type of composition of functions, as long as you have an inner and an outer function. So let's suppose for part B, instead of the square root of 3x squared minus x plus 1, what if it were y equals the sine of 3x squared minus x plus 1? So in that case, again, what you want to mentally do is to compare it to what if it had been the sine of u? What would you have done to find dy du? What you would have done is apply the rule that says the derivative of the sine is the cosine. So you would have gotten cosine of u. Alright, so what do we do when we have something other than a single variable inside here? We're going to pretend it was just a single variable, but keep it there, and then compensate by multiplying by the derivative of the inner part of the function. So our derivative is going to be the cosine of, and then we're going to keep that the same, 3x squared minus x plus 1, times, since it wasn't just an x or just a u, we're going to do derivative of 3x squared minus x plus 1. So in other words, that's y prime equals cosine of 3x squared minus x plus 1 times, and then we're going to have the derivative of 3x squared is 6x, and derivative of negative x is negative 1 again. Alright, and often we write the 6x plus, or 6x minus 1 rather, part out front just to make sure everyone's clear that it's not in the argument of the cosine, but it doesn't really matter. Either format is fine. There's no perfect way, no one right way. Okay, so that would be another example of the chain rule, but using a trig function. Let's do one more. So part C, what if we had f of x is equal to, and then we had the natural log of 3x squared minus x plus 1. Alright, so you can see this is a composition of functions. We have this polynomial function, 3x squared minus x plus 1, that's inside of a logarithmic function. And so that tells you it's going to be a chain rule. But what you need to do first is just think, what if it had been f of u equals natural log of u? What would my rule have been then? So remember, the derivative of a natural log is 1 over the argument, 1 over u. Alright, so in this case, it's going to imitate this, but again, to compensate for the fact that it's not just an x or not just a u, we're going to multiply by the derivative of the inner part of the function. So it's going to be f prime of x equals, we're going to have, instead of natural log of 3x squared minus x plus 1, what does the derivative of the natural log do? It takes the reciprocal. So it would be 1 over u, but in this case it's 1 over 3x squared minus x plus 1. And then multiply by the derivative of 3x squared minus x plus 1. And so we get f prime of x is equal to 1 over 3x squared minus x plus 1 times 6x minus 1. And of course that can be written in the numerator. F prime of x equals 6x minus 1 over 3x squared minus x plus 1. Right, if we thought there was any hope of reducing that, we would try factoring the denominator, but it's definitely not going to factor into 6x minus 1 times something, so we can just stop there. All right, so I want to show you a different notation that you will often see with these rules. So let's just do B and C then. All right, so for B here, what happened was we had y was equal to the sine of something other than x, u. But instead of differentiating with respect to what was in the argument, we differentiated with respect to x, right? This is dy dx that we're finding here. Y prime can also be written as dy dx, and we're differentiating with respect to x. So one way to describe what's happening here is when you have something other than x inside the argument, you take the derivative as if it were just an x in the argument, but then since u is not equal to x, you multiply times the derivative of u du dx. So this is one way you'll see the derivative formula written, and what it is describing is really how you apply the chain rule to that function. Or in this case, if we had f of u equals the natural log of u, but instead of differentiating with respect to u like that, we differentiate with respect to x, then dy dx or df of u dx is going to be 1 over u times whatever the derivative of u is. All right, so this is another way that you'll see the derivative for natural log written. You'll see d dx of the natural log of u equals 1 over u times du dx. And all it is saying is just take 1 over whatever was in the argument, and if it's not an x, multiply by the derivative of whatever it is. Now let's look at some examples where we have to apply multiple rules. So for example, find the indicated derivative and I want to pull an example from chapter 3 here. Okay, so here's our y equals 4x e to the negative 2x minus 3e to the x cubed. Let's see here, 4x e to the negative 2x. negative 3e to the x cubed. Okay, so to find this derivative, I want to observe a couple of things. One, we know when we have a sum or difference, we can just take the derivative of each part of the sum or difference, each term, separately. So we're going to do that. Then to take the derivative of the first term, notice that we have something with an x times something else with an x. And whenever that happens, you have to use the product rule. And then over here on the right, notice that we don't need a product rule because there's only one function of x here. But the power is not e to the x, it's e to the x cubed. So that is a composition of functions. So that means that we're going to need the chain rule. All right, so let's go ahead and start with that. Now, in the process of doing the product rule, we're actually going to have to do the chain rule as well. So we'll have to do the chain rule twice in this problem. Let's see how that works out. So first, let's remember the product rule. If you have y equal to some first function capital F times a second function capital S, then y prime is going to be the first function times the derivative of the second plus the second function times the derivative of the first. All right. We also need to remember that the derivative with respect to x of e to the x is going to be just e to the x. But the derivative with respect to x of e to anything other than x is going to be e to that power times the derivative of whatever it was to compensate for the fact that it wasn't an x. So, in other words, this is the chain rule version of the derivative of e to the x. All right, so in our product rule, the first function is the 4x, so this is our f, and the second function is our e to the negative 2x. So if our first function is 4x, its derivative, f prime, is just 4. And if our second function is e to the negative 2x, then its derivative will require a chain rule because we have something other than x in the exponent of the e. So we're going to take the derivative of that. Derivative of e to a power is just e to that power times the derivative with respect to x of whatever that was. So that would be the derivative of negative 2x, which is just negative 2. So this derivative of this second function is negative 2e to the negative 2x. Okay, so we have all the components we need for our product rule to take the derivative of the 4x e to the negative 2x part. So I'm going to go ahead and recopy my function down here. We have y equals 4x e to the negative 2x minus 3e to the x cubed. Then y prime is going to be, focusing on this part first, the first function f, which is 4x, times the derivative of the second function, which is negative 2e to the negative 2x, minus the second function, which is e to the negative 2x, times the derivative of the first, which is just 4. Now let's move on to the second term. Taking its derivative, we're going to have to use the chain rule. The negative 3 stays the same. The derivative of e to a power is e to that power. And then, since that power wasn't just an x, we multiply times the derivative of x cubed. So we have y prime equals, let's clean this up a bit, that's negative 8x e to the negative 2x minus 4e to the negative 2x. And then we're going to have the derivative of x cubed here is 3x squared. So if you multiply that times negative 3, you get negative 9x squared e to the x cubed. Now there's no one perfect way to write this expression, this derivative, so I'm just going to leave it in this format for now. It's possible that you would be required to write your exponents as positives moving into the denominator, but again, I don't see anything, for example, in common to all three to factor out that would make the expression look nicer. But you could play around with that, but there's not one perfect way to write the answer. Okay, so we're going to do one more like that and then we'll be finished. One more, meaning one more that involves a chain rule together with another type of rule. We don't have the one I was looking for. Let me go back over here. All right, let's use this one. Part B. We have f of x equals x over the cubed root of x squared plus 4. Okay, so the first thing you want to do when you see a root and you have to take a derivative, we don't have a rule for roots, so we're going to change it to an exponent format. So I'm not taking a derivative right now, I'm just writing it algebraically with a different symbol. So I'm going to use this as, instead of using rather the cube root, we're going to use power of 1/3. All right, the next thing I'm going to do is observe which operations are going on. I have something with an x divided by something with an x. That's quotient rule. And remember, for the quotient rule, you're going to think of the function f as the top divided by the bottom. And so f prime will be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. All right, in this case, what's our top function? Our top function, t, is just x. And what's our bottom function? Our bottom function is x squared plus 4 to the 1/3 power. We're going to need our top function, our bottom function, and the derivatives of each. So we need t prime. Well, the derivative of x is just 1, so that's easy enough. But the derivative of b, we have a power, something other than an x as the base. So we're differentiating with respect to x, so that means we're going to have to use a chain rule. So we're going to take the derivative as though it were just an x instead of an x squared plus 4 by bringing the 1/3 out front and subtracting 1 from it. But we're going to leave that x squared plus 4 plugged in, and then to compensate for the fact that it wasn't an x, we're going to take the derivative of x squared plus 4 and multiply it. So b prime, the derivative of the bottom, is 1/3 x squared plus 4 times the derivative of x squared is 2x, derivative of 4 is 0, so we don't need that. Oh, and I still need my power here. We don't want to lose that. Okay, so using the pattern bottom d top minus top d bottom over bottom squared, we have that the derivative of our function f is going to be the bottom, which is x squared plus 4 to the 1/3, times the derivative of the top, which is just 1, minus the top, which is just x, times the derivative of the bottom, which is 1/3 times x squared plus 4 to the negative 2/3 times 2x. All of this is going to be over the bottom squared, so x squared plus 4 to the 1/3 squared. All right, so this looks very messy, but there's something you can do, and it works probably 80% of the time on these problems. What you want to do is to think of the numerator as two big terms. Here's one term, here's another term. And you want to factor out any common factors from the two terms. And this is going to help you to simplify the expression. You also want to factor out any fractions, even if they're not in common. So let's try that. So we have f prime of x equals, okay, we have a common base, which is x squared plus 4 and x squared plus 4. But what power do you factor out? So I just want to go off to the side here and remind you of something. If we had, say, x squared minus 5x cubed, what power of x could we factor out that's in common? You would factor out the lowest power, right? So you would take out the x squared, and that would leave you with 1 minus 5x to the first. Notice 3 minus 2 leaves a power of 1. You factored out the lowest power. We want to factor out the lowest power of x squared plus 4 as well. So what we're going to be factoring out is x squared plus 4 to the negative 2/3. Negative 2/3 is less than 1/3, so factor out the lowest power. Now I also said factor out any fractions that you might have. So you see how we have a 1/3 here? I'm going to factor that out as well. Remember, that has the effect of dividing by a third. So let's see what's left behind when I factor out the lowest power and the 1/3. So in the first term, since I've divided it by 1/3, that's like multiplying it by 3. So we're going to have a 3. And then we're going to need 1/3 minus negative 2/3. When you factor out negative 2/3, just like when I factored out x squared over on the left in green here, the x squared, I subtracted 3 minus the power of 2 to see how many powers of x were left. So for this power here, we're going to have to subtract 1/3 minus what we took away, which was negative 2/3. So that's going to add up to 3/3 or 1. That often happens, that the exponent goes away when we do this. So x squared plus 4 to the first power is left, and we don't really need to write the 1. All right, and then in the second term, we've removed the x squared plus 4 to the negative 2/3. We brought that up front. We removed the 1/3, and what else is left? Just negative x times 2x. All right, now that's all over x squared plus 4 to the 1/3 squared. When you raise the power to a power, you multiply the exponent. So that's just going to be x squared plus 4 to the 2/3 power. All right, now let's see why this is helpful, what we just did. So inside these parentheses here, the brackets I should say, we now have 3x squared plus 12 minus 2x squared. The 3x squared and the 2x squared combine, leaving just an x squared plus 12 in the brackets. Okay, and I'm going to bring my x squared plus 4 to the negative 2/3 down below, and I'm also going to think of this as this 1/3, bringing it out front. So the 1 is in the numerator and the 3 is in the denominator. So this is going to be 3 times, and we're going to have x squared plus 4 to the positive 2/3 times the x squared plus 4 to the positive 2/3 that was already there. Okay, so it's starting to look much better now. And we can multiply these two together by adding the exponents. So we have f prime of x equals, and we have x squared plus 12 over 3 times x squared plus 4 to the 4/3 power. So this is our derivative. So oftentimes when you use a quotient rule, and in the process you have the chain rule for a power function, it's very helpful to, at this step, factor out. Don't try to distribute or do anything like that. You're going to factor out whatever's in common. You're going to factor out the lowest power of whatever base and any fractions. The algebra can be challenging. Most of the time I see students get to the step where they have found the derivative, but the simplifying can trip them up. Okay, well, I hope this chat was helpful to you. If you did, please remember to give it a thumbs up. When you like it, it helps other students to find the video.